better scalability. So let's look at why STT-MRAM is more attractive. So the structure is very similar as the previous RAM or phase change memory with this 1T1R, and you can have the MTJ structure to the contact of the drain via. And the benefit of this STT-MRAM, in principle, you can scale down to like 6F² if you use the DRAM design rule, because this is essentially 1T1R structure. It's like 1T1C for the DRAM. But of course, in reality, we haven't achieved like 6F². We will talk about the limitations there. But in principle, you can do 6F². So this is the let's say development of the MRAM back from like 2000. So in the early stage, early 2000, industry focused on the Field-MRAM, and we have this like 60 megabit demonstrations. But after that, the STT-MRAM is rising up, and the industry switched to the STT-MRAM, and I think the trend continues. And recently, I think there are 256 megabit demonstrated, and recently, I think like 1 gigabit from Everspin also demonstrated. So this is a trend. So let's look at the advantage of the STT over the Field-MRAM. The key advantage is the scalability of the current. Because this conventional Field-MRAM, we need to use the large current on this red line here. You pass the current to generate this surrounding field, magnetic field. As you scale the technology node, you get smaller cross section for this red line. So you need to actually pass higher currents to generate the field, or let's say the current density will increase. So here, the current density will increase as you scale, because the scaled wire, you need to pass more current to generate this surrounding field. And then for the STT-MRAM, the red current directly pass through the MTJ structure. And it's very nice that when you scale the technology node, the area of the MTJ scales, so the red current also scales in proportion to the area, because the current directly goes through the MTJ structure. The first one relies on fringing field, so it's not good for scaling. So this is the key advantage for the STT-MRAM compared to the conventional Field-MRAM. So this is the STT-MRAM. Now you can directly use a current to change the resistance. But still, the readout mechanism is the same. So the readout ratio, which is this TMR, is still like 100 to 200%. So this one does not change, because what you changed is the write mechanism for the MTJ structure. But for the read mechanism, is still the same. You read the difference of those two resistance. So let's look at the principle of the STT switching. So here, let's look at the first one. This is if you want to switch from the anti-parallel state to the parallel state. So initially, let's assume the pinned layer is to the left, and initially the free layer is to the right. Now you want to switch the free layer from the right to the left. So what you want to do here is to pass a large current. You pass current directly through this MTJ structure. So you pass current, and that means you are injecting the electrons this way. Because you know the electron flow is opposite to the current by definition. So when the electrons coming from this transistor go into the MTJ structure, so the transistor is not polarized. Transistor current should have both electrons spin up and spin down, or in this case, spin to the left or spin to the right. So this current is mixed of the two spin states. So you will have those two electrons go into this structure. And the spin to the left electrons, when they turn low to this free layer, it will pass this free layer, because the free layer is pointing to the left, so they have the same polarization as this incoming electron. But for the spin to the right electrons, when it turns low to the free layer, because free layer is to the right. Oh, sorry, I think I made a mistake here. This is a little bit complicated. So I think this one, the electrons pointing to the right, when they turn through to the free layer, because free layer is pointing to the left, so they don't match. This one is pointing to the right, and the free layer is the free layer initially is pointing to the right, right? Spin right could not go through in the layer. Maybe C. Oh, okay, I got it. Okay, got it. So let me redo this. Okay. A little bit tricky. So again, let's start from here. When the electrons go into the structure, it has both spin to the left and spin to the right. And first, the electrons need to go through this pinned layer and then turn out to the free layer. But when the electron goes into this pinned layer, because pinned layer is to the left, so electrons pointing to the left will pass because they have the same polarity. But the electrons pointing to the right will be reflected. It will not allow the electrons pointing to the right to go through the pinned layer, because this pinned layer may be very thick. The reason is pinned because it's thick, so you cannot change the orientation of the pinned layer. So the electrons pointing to the right will be reflected, will not turn through the barrier. Only the electrons pointing to the left will turn through this barrier and then enter the free layer. So as the electrons enter the free layer, as it travels through the free layer, this pointing to the left electron will insert a torque to the free layer to flip the free layer's orientation from the right to the left, because the electrons here are pointing to the left, and you have so many electrons pointing to the left travel through the free layer. It's like you insert a torque to the free layer to flip to the left. So this is the force those electrons apply to the free layer. Actually, it's the torque. So this is how you flip this one. And then for the other case, from the parallel state to the anti-parallel state, so we can do similar analysis here. So initially, both layers are pointing to the left, and now we need to switch the current direction for the set and reset. Then we need to flip the current direction. This is bipolar switching. So we'll apply current this way. That means electrons will come down from the bit line. And from the bit line, initially you have both spin left and spin right electrons go into the MTJ structure. And then here, both of them will turn through the free layer, because free layer may be very thin. It cannot block the electrons to the right. So let's say electrons to the left first. So since this is initially is pointing to the left and the electrons pointing to the left, so they are aligned. So this will be passed through. But for the electrons pointing to the right, it enters to the free layer, but free layer is thin, so free layer cannot block the electrons to the right. So these electrons to the right will keep traveling and turn through the barrier and reach the pinned layer. When it reaches to the pinned layer, because pinned layer is pointing to the left, so these electrons pointing to the right will be reflected back, because the pinned layer is thick, so it cannot travel through, so it will be reflected. So once those electrons are reflected back, so they are pointing to the right, so those electrons will insert a torque to the free layer, try to flip the free layer to the right as well. So this is how the parallel state switch to the anti-parallel state. So any questions?
Why not just say the electron spin to the right, when it passes through the free layers, we'll give it a torque, try to flip it. Why do we need to talk about those electrons?
New reflective?
Yeah.
So I think initially the free layer is thin, so the electrons can travel through. And you need this reflected electrons to insert additional torque, because I think initially the torque is not large enough. You need the electrons bounce back and then insert additional torque to flip.
Are these just hypotheses, or people have already?
This is from the physics, I would say, right? So then how do you visualize? This is very difficult, right? So I think there's some measurements to look at this, but I'm not expert in those materials and characterizations. Yeah. But from physics, yes, it's like this. So as you can see, there will be a symmetry between those two cases. They're not, let's say, exactly the same. So that means the anti-parallel to parallel or parallel to anti-parallel switching actually will have some asymmetry in terms of the current, rate current or the rate speed. They may be a little bit different, because one is relying on the direct pass-through electrons, the other one relying on the additional reflected electrons. So they may have some asymmetry between those two. So that means STT-MRAM, when you write 1 to 0 and 0 to 1, they are not the same in terms of the write current or the write speed. 1 to 0 or 0 to 1 switching are not exactly the same. So this is a little bit complicated. I don't expect that you really understand this one. And this is even more complicated into the physics. I will not spend too much on this. But actually you can understand this by simply look at this kind of a precession diagram. So the spin up and spin down state, actually you can think this is a sphere here, and then you have this spin, it's like an arrow, and then when you apply the current to the spin state, it's like you are going to have this kind of rotation. And then if you have large enough current, then this rotation will happen, and this is called the precession if you refer to the mechanics. And then once it flip to the other side, then it will flip the spin state down. So if you look at the trajectory, if you do this rotation, precession, and then actually the spin state will follow this kind of trajectory when they switch from the spin up to the spin down state. Again, this is the physics, very hard to visualize. So there are a few points I want to make. Okay. First, there is the so-called damping effect. So that means what? Means when you have some current to basically disturb the state of the spin, it starts this kind of rotation. But you need not enough current to make this rotation to at least make this arrow cross this hemisphere, this circle, right? So if you remove your current, then the spin state will damp to the original state due to the friction. This is the damping effect. If the current is not large enough, then after you remove the current, the spin state will return to the original state. So in other words, if the current is large enough, once this pass this circle, if you remove the current, then it will converge to the other state. So for this kind of phenomenon, so what kind of memory, you think is similar to this? Any idea? We talked about that before. SRAM, right? If you recall SRAM, the butterfly curve, right? If you have noise, small, then after you remove the noise, then it will go back to the original state. If you have enough disturbance, then it will go to the other state. This is exactly the same effect here. So, but in this case, there are some effects due to the thermal noise. So even you have current, then rotate this spin, and sometimes due to the thermal noise, even the rotation only points the spin to here, but due to the noise, it may flip to the other side. So this is due to the noise, and this is a thermal process. So here, this equation, very complicated, but basically it describes the theta, which is this angle, And d theta over dt is the change, or let's say the speed of this rotation in terms of the angle change. And then this angle change rate as a function of the current. So if you have zero current due to the thermal noise, so actually this spin state will thermally disturb a little bit. It may flip down, but sometimes due to thermal noise, it will flip back. So sometimes this d theta over dt, sometimes it's negative, sometimes positive, but overall, it will remain, on average, pointing to the up. But if you apply current, then you will try to flip this spin state, this angle. So here is the critical current. That means if your current is larger than this critical current, then the d theta over dt is always positive. It's always positive. Always positive, that means you are going to always try to flip, right? Positive means that this angle is going to increase. The rate positive means the angle is going to increase. If you keep the d theta over dt to be positive, then eventually it will flip. So this is the critical current you need to apply. But if you are less than the critical current, you may flip the state, but it depends on luck. Right? Sometimes you may have thermal noise to flip it. Sometimes you may not have that. So this is a stochastic switching if it's below the critical current. Okay, so this is too much physics here. I will skip that, but it turns out this will affect the device characteristics of your STT-MRAM. I will talk about that later. So before that, a very brief discussion on the STT materials. Actually, the STT effect was theoretically predicted by those two papers in 2001, purely by solving the physical equations. So they predict that it will have this kind of phenomenon in certain structure of certain materials. And experimentally, later, in 2004, this STT effect was demonstrated by two groups, one from IBM and one from Japan. So this is the paper from those two. And then after 2004, this becomes real. This effect becomes real. Then the industry jump in, and then you see the rise of the STT-MRAM chip demonstrations from 2006-07. So it's pretty fast actually from the discovery of this effect to the kind of prototype. So the key parameters for the device design is that the current density to flip the state and the readout margin, this is TMR, and the thermal stability, this relates to the data retention. I will talk about that later. And the breakdown voltage, so this will affect lifetime and endurance. I would say the key challenge for the STT design is to achieve low rate current density and high thermal stability at the same time. This is very hard to achieve because the two states you can think is an energy barrier between the spin up and spin down state. So if you want to write those cell, that means you are going to change these two states by clamping over this barrier. But for the data retention, you don't want to change the state. So you want this barrier to be high for the data retention, for thermal stability. but you want the barrier to be low for efficient write operation. So essentially, this is a fundamentally conflict. As we discussed before, if you recall this principle we discussed before for the SRAM, and you recall the 6-transistor SRAM cell, the read and write conflict with each other, right? Fundamentally, this is a problem for all kinds of memory, because for memory, write operation you want to change the data, and the read operation you don't want to change the data. You want to maintain this for a long time. So then this is a conflict.
So the current density is the current in the cross section?
Yes, that the current density is the current passing through this this area, this area of this.
Then you can make this area as small as possible, then you have very high current density to achieve the right.
No, the current density, let's say given a certain material here, the current density is the same. Okay, you scale the area of your MTJ structure from the top view. You scale the area, your current scale, proportionally. The current density is a constant for a given material system. Of course, you change the stack material and that will change. But if you just scale the area, it will not change the current density.
So for the pin layer, how do you make sure all your spin states are the same and it doesn't change while you read or change the other layer?
Oh, this is the, I'm not expert in that, but as you see earlier slides, right, the very complex structure, you build multiple layers, and then those layers help to stabilize the pinned layer. So it's very complicated to make that happen. But of course, that is to, let's say, to pin the layer to a certain degree, right? Of course, if you pass too large current, or if you have this STT-MRAM chip in a very strong external magnetic field environment, then of course the data will be lost. That's actually a concern for the STT-MRAM. If you use that chip close to some external magnetic field in medical environments, then it will not work. Okay. So the pin layer will not pin. Okay.
Can you also explain a little bit more? When the second slide you show a multi-layer diagram, there's one layer called storage layer in between.
Storage layer. That is free layer.
Oh, okay.
Yeah, storage layer, because you store data there, 0 and 1, depending on the direction of that layer.